Welcome back to this session. So today from this session onwards we'll be starting a numerical. So let us get going with the first numerical. A timber beam 150 mm wide and 300 mm deep is simply supported over a span of 4 meter. It carries UDL 10 kN per meter over entire span. Find the maximum and minimum bending stress induced in the section. Draw bending stress distribution diagram. Also find radius of curvature if E is equals to 1.4 kN per mm square. Now in this case, the diagram of a beam is not given, so reading the question we need to first draw the diagram of the beam, and then after that analyze the beam and find stresses induced in both the section, that is in a tension zone as well as in compression zone. So let us see how we can solve this numerical. So for this numerical, a timber of a section 150 mm wide into 300 mm deep is given. So let us draw the section first. Timber section, which is 150 mm wide and its depth is 300. mm deep is given. Okay, and then it is simply supported over a span of 4 meters. So it is simply supported. So I'm going to draw the simply supported diagram here. Simply supported over a span of 4 meters. So its span given is 4 meter. Let this be A and B. Okay, and it carries a UDL of 10 kN per meter over the entire span. So आप यहाँ से entire span के लिए UDL carry करते हैं, which is equal to 10 kN per meter, right? And then for this we need to find maximum and minimum bending stress induced in the section, and then after that we need to draw bending stress distribution diagram and also find radius of curvature, and the value of E, Young's modulus E, is given equal to 1.4 kN per mm square. So value of E is given this much. Now we need to draw a bending stress distribution diagram. So bending stress distribution diagram हम ये section से draw करेंगे. तो ये symmetrical section है. Symmetrical section के लिए stress produced in compression will be equal to stress produced in tension. So let us see how we can solve this one. So we need to find stress, right? Stress equal to question mark. Now from the flexural formula, from this flexural formula, which is equals to m by I equals to sigma by y. This is a flexural formula. Now this flexural formula I can find this value of sigma. So from here sigma will be equal to m by I into y. We'll get this formula, right? अब यहाँ पर हमें क्या क्या फाइंड करना है? हमें मोमेंट फाइंड करना है. We need to find maximum bending moment, then we need to find moment of inertia, then we need to find y, which is depth, right? So let us start by finding the maximum moment. This is the bending moment. Okay, so maximum bending moment will be equal to, now this is a simply supported beam and it carries a UDL over its entire span. So the maximum bending moment for this simply supported beam will lie at WL square by 8. Okay, now from here W is equal to 10 kN per meter. So we have 10 kN per meter into length of the beam given is 4 meter. So 4 square divided by 8. from here you will get equal to 20 kilonewton meter. और आप ये किलोन्यूटन को न्यूटन पे और मीटर को mm पे कन्वर्ट किया तो you will get 20 into 10 raised to power 6 Newton dot mm. Okay, so we have this. Now let us find moment of inertia I. For this rectangular section, moment of inertia I will be equal to along x direction, क्योंकि ये x direction पे find कर रहे हैं, will be equal to BD cubed by 12. This is from unit 1. You need to remember, okay? So here B is given equal to 150, depth is given equal to 300 cubed by 12. So from here you will get equal to 337.5 into 10 raised to power 6 mm raised to power 4. So this is the moment of inertia. Now after this you need to find y. Y will be equal to this depth. Okay, this is y. So how much will y be? Y will be equal to d by 2. So how much is d? Total depth is 300 divided by 2. So you get 150 mm. Right, so you have 150 mm. Now you have all the values. Now let us put it in this equation and find stress. So stress will be equal to m is 20 into 10 raised to power 6 divided by I is 337.5 into 10 raised to power 6 into y is 150. So from here you will get stress equal to 8.89 Newton per mm square. So you have found the stress. Okay, you found the stress. Now this stress which you have found, this stress will be equal to stress in compression zone will be equal to stress in tension zone, because this is a symmetrical section which is equal to 8.89 Newton per mm square. Okay, so now let us find this in second section of this question. We are asked to find radius of curvature. Before we find radius of curvature, let's draw the bending stress distribution diagram. So drawing this bending stress distribution diagram, straight line, and then here, and this should be equal. It will go right from in between this section. So this here is sigma t tension zone के लिए, it is coming 8.89 Newton per mm square, right, which is from here to here. अब यहाँ से यहाँ तक is sigma c. So sigma c is equal to again 8.89 Newton per mm square. Okay, so this is your bending stress distribution diagram. Okay, now let us find the radius of curvature. To find radius of curvature, r. अब ये r कैसे find करेंगे? Again from the flexural formula, which is m by I equals to E by R. This is also a flexural formula. अब यहाँ से we can find r. So for r, from here will be equal to E by m into I. You will get this formula here. Now from here, r is equals to, how much is E given? E is given 1.4 kilonewton per mm square, right? So ये जो ई किलो न्यूटन पे दिया है उसको हम न्यूटन पे कन्वर्ट करेंगे, तो कितना होगा 1.4 इंटू 10⁻³ अब ये हो गया न्यूटन पर mm स्क्वायर डिवाइडेड बाय मोमेंट वी फाउंड इक्वल टू 20 इंटू 10⁻6 इंटू आई इज इक्वल्स टू 337.5 into 10⁻6, right? So this from here you will be getting E equal to 23.62 meter. So the radius of curvature is equal to 23.62 meter. So I hope this numerical is clear. Let's solve the second numerical. A timber beam 200 mm wide and 300 mm deep is simply supported over a span of 3 meters. It carries an UDL of 12 kN per meter over the entire span and a central point load of 10 kN. Determine maximum bending stress induced in section and draw bending stress distribution diagram. Again in here, जैसे हमने first numerical पे solve किया था, so वैसे ही हमें यहाँ पर भी पहले जो given है उसको draw करना पड़ेगा. Then after that we need to find the maximum bending stress induced in the section. So let us get started. For this numerical also, a timber beam of 200 mm wide and 300 mm deep is given. So it is 200 mm wide and 300 mm deep. So this is 200 mm wide and its depth is given equal to 300 mm. Okay, and what else is given? It is simply supported over a span of 3 meters. So it is simply supported. So here simply supported and its span is 3 meters. Okay, and it carries a UDL of 12 kN per meter over the entire span. So entire span के लिए 12 kN per meter UDL it is carrying 12 kN per meter over entire span and a central point load of 10 kN. Central. अब ये 3 meter के आधा 1.5 meter पे it is carrying a point load. So at 1.5 meter it is carrying a point load here. Okay, this point load, intensity of this point load is 10 kN. Let this be A and B, right? अब यहाँ से we are asked to find maximum bending stress induced in the section and draw bending stress distribution diagram. Now we need to find a maximum stress. जैसे हमने first numerical पे find किया था वैसे हम ये भी find कर सकते हैं. तो from flexural formula which is m by I equals to sigma by y. यहाँ से we get sigma is equals to m by I into y. ये मिलते हैं, right? तो फिर हमें यहाँ से m, I और y find करना है. So how can we find this maximum bending moment here? Bending moment maximum, right? The first case is with a point load. अगर point load है तो it will be at WL by 4 और second पे UDL चल रहा है. So simply supported beam के लिए maximum bending moment for a simply supported beam carrying a UDL will be at WL square by 8. Now how much will you get from here? W here. This one is a small w. Okay, so this W, capital W here is a point load here, 10. So I have 10 into 3, total length is 3, right, by 4 plus. नाउ यूडीएल के, ये यूडीएल का है स्मॉल w, सो यूडीएल कितना है 12 इंटू लेंथ इज 3 स्क्वायर डिवाइडेड बाई 8. दिस विल गिव यू exactly equal to 21 kilonewton meter. अब ये किलो न्यूटन को न्यूटन पे कन्वर्ट किया तो कितना होगा 21 इंटू 10⁻3, और ये मीटर को पे कन्वर्ट किया तो अगेन इंटू 10⁻3 विच विल बी इक्वल टू 21 इंटू 10⁻6 न्यूटन ये हो जाएगा. Right, now we have found the moment. Now let us find the moment of inertia I. For this rectangular section it will be BD cubed by 12. So how much is B? 200. D is 300 cubed by 12 will be giving you equal to 45 into 10⁻7 raised to power 4. This is what you will get. Now let us find y also. So y will be equal to y, यहाँ से अगर न्यूट्रल एक्सिस ऐसे जा रहा है, this neutral axis line, और y will be this much, right? तो y कितना होगा यहाँ से, it is d by 2 which is equals to 300 divided by 2 which is equal to 150 mm. Now let us find the stress. Maximum stress here is a stress in tension zone. So you have stress in tension zone will be equal to moment. We will put it in this equation here. So m kitna mila? M 21 into 10⁻6 divided by I kitna mila? 45 into 10⁻7 into y is 150. So this will give you stress equal to 7 Newton per mm square. Okay, so this is the stress. Now here this portion here is yt and यहाँ से आधा इतना portion is yc. We were finding stress in tension zone, so यहाँ पर क्या होगा, this y will be yt also. Okay, here it will be yt if we are finding for sigma t. So let us draw the stress distribution, bending stress distribution diagram. So from here you will be getting, okay, and since this is a symmetrical section, you will have this. So यहाँ पर this is the maximum which is in positive, right? Sigma t came equal to 7 Newton per mm square, right? and यहाँ पर sigma c भी उतना ही आएंगे 7 Newton per mm square, और ये यहाँ से यहाँ तक होंगे. Okay, so this is the stress distribution, bending stress distribution diagram. Okay, so I hope this numerical is clear. Let us solve the third numerical. A beam of cross section 100 mm into 200 mm is simply supported at both ends. It carries two concentrated loads of 100 kN each, acting at 2 meter distance from each support. Span of the beam is 7 meter. Determine maximum bending stress induced in the beam. So let us see how we can solve this numerical. In this question, a beam of cross section 100 mm into 200 mm is given, right? So 100 mm is its width, and 200 mm depth. So its width is 100 mm and its depth is given equal to 200 mm. अब यहाँ से what it is saying, it is simply supported at both the ends. So it is simply supported at both the ends, and it carries two concentrated loads of 100 kilonewton each at acting at 2 meter distance from each support. अब ये support से 2 meter distance पे I have a 100 kilonewton load, and again from this support here, this point at 2 meter also I have 100 kilonewton load, right? So let me name this at A point and B point. तो यहाँ से यहाँ तक it is 2 meter distance पे है, और यहाँ से यहाँ तक पे it is at 2 meter distance, right? And let me name this point as C and this point D. And the span of the beam is 7 meter. So the total span यहाँ से यहाँ तक the span is 7 meter. Okay. Now we have to determine maximum bending stress induced in the beam. तो हमें फिर से फ्लेक्सुरल फार्मूला से हमें सिग्मा निकाला, तो सिग्मा will be equal to m by I into y, ये मिलेगा हमें. तो यहाँ से हमें फिर मोमेंट, मैक्सिमम बेंडिंग मोमेंट फाइंड करना पड़ेगा, देन मैक्सिमम बेंडिंग मोमेंट, देन मोमेंट ऑफ इनर्शिया एंड y, राइट. सो अब यहाँ पर मोमेंट, मैक्सिमम मोमेंट फाइंड करने के लिए, ये मोमेंट एट C एंड मोमेंट एट D फाइंड करने के लिए, लेट अस डू इट एज वी डिड इन यूनिट नंबर 4. सो यहाँ पर RA रिएक्शन आएंगे, RA यहाँ पर RB, right? So RA plus RB will give you 100 plus 100, which is equals to 200 kilonewton. Now if I take this point as my reference point for summation of moment about A equals to 0, now I want to find moment at C. Moment at C will be equal to, I need to find moment at C, right? So if I keep this moment at A equals to 0, from here I'll get RA into distance, starting distance is 0, then ये जो है ये C का, it will go in anti-clockwise direction, so minus, it will go in clockwise direction, so plus 100 into the distance from C to A is 2, right? Next ये D point का भी ये clockwise direction पे जाएंगे, right? So I have again plus 100 into, अब D से A तक डिस्टेंस कितना होगा, ये बीच का डिस्टेंस कितना होगा, अगर 2 plus 2 4 है तो ये रिमेनिंग 7 minus 4 I have 3 meter, so 3 plus 2 5, so distance is 5. Then ये RB ऐसे जाएंगे, right? So minus anti-clockwise से RB into total distance 7. So यहाँ से क्या मिलेगा, 100 into 2 I have 200 plus 100 into 5 500 equals to, ये इसको मैं उधर भेजूंगी तो पॉजिटिव हो जाएगा 7 RB. So यहाँ से RB will be equal to 500 plus 200, 700 divided by 7 will give you exactly 100 kilonewton load. So यहाँ से RA will be equal to 200 minus 100 will give you 100 kilonewton each. So RA पे 100 kilonewton आया, RB पे भी 100 kilonewton आया. Now moment at C फाइंड करने के लिए, moment at C ये पॉइंट पे फाइंड करना है, राइट? तो हमें A से C तक जाएंगे, तो कितना होगा, A क्लॉकवाइज डायरेक्शन जा रहा है तो 100 इंटू डिस्टेंस A से C तक 2 मीटर ही है, सो 2, so you get 200 kilonewton meter. Similarly मोमेंट एट D फाइंड करना है. अब आपको यहाँ ये पॉइंट से यहाँ तक जाना है, तो क्या करेंगे, यहाँ से ये A रिएक्शन RA टुवर्ड्स D विल गो इन अ क्लॉकवाइज डायरेक्शन. C पॉइंट पे जो ये पॉइंट लोट आ रहा है D के तरफ, ये ऐसे घूम कर जाएंगे, और ये कौन सा डायरेक्शन हुआ, एंटी क्लॉकवाइज. सो आई हैव 100 into यहाँ से यहाँ तक distance is 5, then ये point load is going anti-clockwise, so minus 100 into remaining distance is 3 D तक. तो यहाँ से कितना मिलेगा 500 minus 300 will give you again 200 kilonewton meter. So moment at C पे 200 आ रहा है, moment at D पे 200 आ रहा है. तो मेरा bending moment maximum will be equal. Maximum moment will be at this point. It will not be plus here, it will be equal to moment at C point पे भी maximum आएंगे, D point पे भी maximum moment आएंगे. तो it will come moment at C कितना आया 200, so I have 200 kilonewton, and moment at kilonewton meter, moment at D कितना आया, again I have 200 kilonewton meter. So दोनों ही maximum points है. Okay, so I have maximum bending moment is equals to 200 kilonewton meter. And now let us find moment of inertia I. So moment of inertia I about I axis will be equal to BD cubed by 12, which will be equal to 100 into 200 cubed by 12. This you will get 6.66 into 10 raised to power 7 mm raised to power 4. अब यहाँ से मेरा if my neutral axis is lying at this section, neutral axis, this point is YT and this is YC. See right? अब हमें maximum bending stress induce जो हो रहा है बीम पे वो फाइंड करने के लिए बोला है. तो maximum कहाँ पर होते हैं, टेंशन जोन पे, पॉजिटिव, right? So YT will be equal to D by 2, which is equal to 200 divided by 2 is equal to 100 mm. Okay, now let us find sigma will be equal to m by I into y. So m कितना है, m we got equal to 200 into, अब यहाँ पर किलो न्यूटन पे है, किलो न्यूटन को न्यूटन पे कन्वर्ट किया तो into 10 raised to power 6, I mean into 10 raised to power 3 न्यूटन पे कन्वर्ट हुआ. अब मीटर को mm पे कन्वर्ट किया तो into 10 raised to power 3. ओके, सो ये mm पे कन्वर्ट हो गया. सो ये क्या हुआ, ये पूरा इसका वैल्यू इज इन न्यूटन डॉट mm. ओके, डिवाइडेड बाय you have Ix is 6.66 into 10 raised to power 7 into y is 100. Now यहाँ से आपको you will get exactly equal to 300.3 Newton per mm square. So this sigma here is equal to sigma t, ये yt लिया है, sigma t, right, is equal to sigma c is equal to 300.3 Newton per mm square. अब यहाँ से बेंडिंग स्ट्रेस डिस्ट्रीब्यूशन डायग्राम ड्रॉ किया तो इट विल कम like this. So यहाँ से यहाँ तक it is sigma t is equal to 300.3 Newton per mm square. यहाँ से यहाँ तक sigma c equals to again 300.3 Newton per mm square. Okay, so अगर आप इसको शेड करते हो तो you can shade something like this. You can shade it in this manner. So I hope this numerical is clear. Coming to the last numerical of today's session, let me read the statement. A joist of 5 meter span, flanges 250 mm wide and 20 mm thick and web 10 mm thick. The overall depth is 500 mm. It carries a UDL of 20 kN per meter over its entire span. Calculate the magnitude of maximum bending stress induced. sketch the stress distribution diagram. So as you can see that this is a symmetrical eye section here, right? So symmetrical eye section ke liye the eye section is given there. Uska flange ka thickness, and then web ka thickness, and then overall depth, everything is given, and the diagram is also shown here. So let us see how we can find its maximum bending stress here, and then draw its stress distribution diagram. So let us get started. So in this numerical, eye section is given, and it says a joist of 5 meter span has flanges 250 mm wide and 20 mm thick. So 250 mm wide and 20 mm thick, and a web of 10 mm thick. So web is also given 10 mm thick. The overall depth is 500 mm. So यहाँ से यहाँ तक overall depth 500 mm. It carries a UDL of 20 kilonewton per meter over its entire span. So it is a simply supported beam, and the span of this beam is given equal to 5 meter span, and it says it carries a UDL over its entire span, right? The intensity of UDL is equal to 20 kilonewton per meter, right? Up यहाँ से they are asked to find magnitude of maximum bending stress induced, and then after that we need to sketch the stress distribution diagram. Now let us start from the flexural formula. From flexural formula we have m by I equals to sigma by y, right? ये flexural formula है. यहाँ से we get sigma is equals to m by I into y. यहाँ से हमें stress मिल जाते हैं. Now how do we find m? What is m here? It is the maximum bending moment, right? तो ये simply supported beam है, इस पे UDL चल रहा है, तो इसके लिए हम maximum bending moment कैसे find करेंगे? It will be equal to WL square by 8. Now how much is W? 20. 20 into L is 5 square divided by 8. From here you will get 62.5 kilonewton meter. और आप ये kilonewton को न्यूटन पे और मीटर को mm पे कन्वर्ट किया तो you will get 62.5 into 10 raised to power 6 Newton dot mm. Okay, अब यहाँ से let's find I. I will be equal to, now we need to make this into a hollow rectangular section, ये I section को. तो कैसे करेंगे? Let me name this as A, B, C and D, और ये अंदर का P, Q, R, S. तो क्या करना पड़ेगा? बाहर का रेक्टेंगल माइनस अंदर का रेक्टेंगल करना पड़ेगा. तो कैसे करेंगे ये हम? बाहर का रेक्टेंगल का बी डी क्यूब बाई 12 माइनस अंदर का रेक्टेंगल बी डी क्यूब बाई 12 ऐसे होंगे. नाउ बाहर का b कितना है? 250 into its depth. Overall depth is 500. So 500 cube by 12 minus. अब अंदर का b कितना है? From here to here it is p से लेकर q तक it is 250 only. 250. अब हमें ये जो अंदर का ये वेब पोर्शन है इसको हमें माइनस करना पड़ेगा. तो ये -10 कर देंगे तब हॉलो बन जाएगी, राइट? इनटू डेप्थ. अब यहाँ से Q से लेकर S तक उनका इनर रेक्टेंगल का डेप्थ है तो ये कितना है? इट इज इक्वल टू 460. सो 460 क्यूब बाई 12. तो अगर आपको इन दोनों को माइनस करते हो यू विल गेट इक्वल टू 657446666.7 mm raised to power 4. Now if you make this into a decimal point as 65.7 into 10 raised to power पे तो कितना होगा 2, 4, 6 and 7 तो it will be 65.7 into 10 raised to power 7 mm raised to power 4 इतना होगा. Okay, now you have found I also. Y कितना होगा? Y will be equal to total depth of the I section divided by 2. So total depth कितना है? 500 divided by 2 से आएंगे 250 mm. Okay, अब यहाँ से let's find, because ये symmetrical I section है तो जो हम सिग्मा फाइंड करते हैं, सिग्मा will be equal to sigma in compression, stress in compression and stress in tension will be same, which will be equal to m by I into y. अब यहाँ से हमें m कितना मिला है? m we got 62.5 into 10 raised to power 6 divided by I 65.7 into 10 raised to power 7 into y is 250. So यहाँ से आपको stress you will get 23.77 Newton per mm square. तो अब यहाँ से हम let's draw bending stress distribution diagram. Okay, this here is stress in tension, so this is equal to 23.77 Newton per mm square. Similarly यहाँ पर stress in compression 23.77 Newton per mm square. Okay, so this is the bending stress distribution diagram. If you shade it, it can be something like this. Okay, so this one here is bending stress distribution diagram. Okay, so I hope this numerical is also clear. This is the last numerical and I'll see you in next class with more numerical. So see you next session.